close to the upper end of the channel bandwidth. Therefore, the RF amplifier must have a very broad frequency response in order to provide equal amplification to the entire 6 MHz bandwidth. Since the frequency response of the RF amplifier stage is so wide, the gain of the stage is somewhat reduced. The ideal frequency response of the RF amplifier will be a flat bandpass, which will allow all frequencies falling within this bandpass to be amplified equally. The response of the leading and trailing edges of the response curve will be such that all frequencies falling outside the 6 MHz bandwidth will be completely rejected. Here you see an RF amplifier stage which uses MOSFET technology. The solid-state device in this circuit is an N-channel dual-gate MOSFET design. Field effect transistors are commonly used for RF amplifier stages due to their low noise, high gain, high input impedance, and their stability at very high frequencies. As you saw earlier, the radio frequency spectrum covers a very broad frequency range. Therefore, the RF amplifier stage will only amplify a narrow portion of this entire spectrum. Since the RF amplifier can only amplify a small portion of the entire spectrum, you will typically find a tuned circuit at both the input and output of the amplifier section. The tuned circuits will be adjusted to a limited bandwidth for the amplifier stage. Since the VHF frequency range extends from 30 MHz to 300 MHz in the TV tuner, shielding becomes necessary, wire length between the components must be shorter, component leads must be shorter, intercapacitance in the active components starts to become more of a problem, connecting wires are made larger to obtain a higher Q for the circuit, and LC circuits are replaced with pieces of bent wire or short pieces of coaxial cable. In general, the RF amplifier circuit becomes much more difficult to work with. Since the RF amplifier stage has incoming voltages of only a few microvolts, internal noise, called white noise or random noise, also becomes a problem. The RF amplifier stage must therefore be able to decrease this internal electrical noise while boosting the incoming RF signal to a level sufficient to override this internal noise, which is usually generated by the mixer oscillator circuits. Specially designed FET devices provide the best low noise performance. At VHF frequencies, it becomes very difficult to combine the oscillator and mixer sections in the same shielded compartment within the tuner assembly due to a phenomenon called oscillator pooling. Oscillator pooling occurs when the local oscillator stage begins to synchronize its frequency with the frequencies of the incoming RF signal. If the incoming RF signal and the local oscillator signal synchronize, a loss of reception will occur. This is due to the fact that the intermediate frequency signal will no longer be produced. As you recall, in order to produce an IF signal, there must be a different signal being produced between the two heterodyne signals. Therefore, to avoid the problem of oscillator pooling, the oscillator and mixer stages are almost always contained in separate compartments within the tuner assembly. The oscillator circuit used in the VHF tuner is designed to produce a VHF AC sine wave at its output. The frequency of the oscillator stage will be placed above the incoming RF signals by an amount equal to the intermediate frequencies used by the television receiver design. The amplitude of the oscillator voltage will be many times larger than the RF input signal in order to obtain the maximum conversion gain. As you might have noticed, the Colpitts oscillator configuration is the most commonly used oscillator circuit in the VHF tuner assembly. The gain-tune coil in the oscillator stage is part of the channel selection circuitry. We will examine the channel selection circuitry later in this video. The mixer stage in the VHF tuner assembly performs the same basic function as performed in the UHF tuner. This stage combines, or heterodynes, the selected RF signal with the VHF oscillator signal to produce the required intermediate frequency signal for the video and sound stages. If the IF frequency of the picture carrier will be 45.75 MHz, the IF frequency for the sound carrier will be 41.25 MHz.